Assalamualaikum warahmatullahi. Jadi discuss tadi is yesterday class. When this paper main process, this paper is fed to the purpose. And it is blended with dilution water and chemicals to form upwelling and stop. The paper sheet formation begins when the stop as we said the composition of the formation. Figure to issues the total of water. Expected the calculation be stream 1, stream 2. Everywhere respected is the position. Part of this source stream 106 is saying to the light water tank. There is liquid water stream 9, other process in the inking partner or DIP. To remove printing in from the non-stop, the inking partner is fed with 751 per hour. It was still through 228 that shuttle from what the 78 of the deep source still 54 ton is then mixed with 27 ton of fresh water through 11. To dilute the stock will come to the regulator in the hospital system. Fresh water stream 10 is also used to dilute the ink chemical in the chemical preparation section CP before the chemicals are sent to the DIP to assist in the removal. In addition, the other process in DIP here also received 201 ton fresh water. Stream 4 is from fresh water collected for production from DIP. 7.53% to the effluent discharge chemical. So again, number 1. So again, the inlet here. This is the demand. This is so 5, 6, 7, plus 9. Is the source. So in sync of source. Calculate the minimum using the water cascade system. So table 1 is So we have how many water in one? Six water in one. So pressing shower, forming others, DIP, CP, and AF. So each have varying concentration. So what TDP is also equal to the same. So what the source is from pressing shower here, and the 5500 ppm. F from number 2 is pumping shower. So both is 230, we total up by 305. And this 9, stream 9, and the 8. So we both. Is it? Yeah, the IP, Silk and the team. 54 plus 415 is 469. So table 2, this is the cascade table. They calculated already. This is the pinch point at 30 ppm. So the actual table is correct. So this this column is concentration. Okay. This is the purity. This is the delta P. So purity they have mentioned. Just to any book. One of it is handbook of process integration, page 265. Purity is equal to 1 million minus C over 100. So if your concentration here is 0, so your purity should be plus 1. And for the second concentration, it should be reducing 1 million minus 20 over 1 million. So for the FT here, so for the first one, 1 million, they are none. So 0. So for the delta P, sorry, let's keep. So for the delta P, it's between 1 and 0. So between this interval, 0 to 20 is 1, consider 1 interval. So the second one. So total you have 7 interval. So 1 minus this, then you get the delta P. So for the 20 ppm here, we have a negative 190 demand. How do we get the negative? Because in this table refer to this table 1. We have to process that have similar concentration, so we just add up. It's negative because of the one, but for C it's positive. Then for the 80 ppm only one, so it's straightforward. Actually one. How about if we have both, like 100 ppm? We have both, so we write for the one, the C, and later on we sum up of the matrices, then we get negative 6.44. And the two is similar. So the 200 is similar. We just add up. The rest is the same. So next is the FC. Available implemented. Similar how they calculate. See. So for FC, refer to paper by 2006. It's available in FC is calculated by multiplying this by no, FC is a cascading. It's a cascading. This one is it's cascading start with zero because normally if we do the analysis, we normally assume the fresh water. This is for water we even spaces with it. So for water we assume zero. So yeah. So at the moment it's the calculator. We start with 138. So we get 148 0 148 minus 990 it's 658 and cascading until the end. So the last number here is equal to the fresh water. This is the fresh water. The pure water surplus here is actually calculated by because in order to identify the pinch, when you do the matrix, the water surplus, there will be a negative. So we cannot use, it's not feasible for the cascade table to have a negative value in the surplus, meaning the water is not enough to feed the system, which we need fresh water input added into. So what happened is the highest negative value from this column, the surplus, will be the pinch point, and that value will be add up here. It's the fresh water, which later causing the sum of the one of the value in the two. If you want to surpass to zero, which from after each point for this process. So pure water surplus is multiplied is multiplication of FC and delta P, FC and delta. So if for 8 times 0.00002, we will get 0.01616 and do the rest. Okay. After that, we need to do the cascading again. So how many you need to cascade? Three. The first cascading is for the delta P, right? With the different purity differences. Then the second cascading is for the FC here with the total up demand plusing. Then here to surplus, no need for cascading, you just need to multiply FC with delta P. Then the last, uh, then you need to do the another cascading. This is the last time we do cascading. So 0.632 plus this, get this minus plus minus 2.0. I hope it's clear. So how do you determine which one is the source? That's one. So how do you know it? That's the first thing. When we do the basket analysis, we need to determine which one is the one. See, which one is the source. So to determine the source versus the one slash C, just need to see that um, the inlet and outlet here. So the inlet for each process when referred to as the demand of the CAF here have to source, sorry, suit to demand, speed of one demand. So when once that one is clear, it's not that hard to do the cascade. So if you do some regeneration, because it's never said density without regeneration. So if you do regeneration, so some of the value you need to regenerate will be appear here. Let's say you can regenerate 80 ppm here. over maybe 100 ppm to what 40 ppm. So meaning another row here will yeah, and you need to recalculate all of it again from P delta P, what else is in there. Then you can see the pinch point will shifted and the value of fresh water will be reduced and the wastewater will be reduced as well. That's what the most, for example, the UTM was very good. All right, that's the only question that is. Now we guess this one is like number three in Elite. Okay. So setting the minimum weekly gas storage target using scheduling system. So this is based on a paper by Professor Dominic Fu from Nottingham, Malaysia, and Prof. Zainuddin Dermanan from UTM. Both are expert in mass pinch analysis, is what you learn now. They come up with their own method how to do it. I'm just here to deliver it. So the typical process integration technique for resource conservation comprises two steps. Setting the minimum resource target followed by result after resource conservation to keep the minimum resource target. Generic targeting technique applicable for various type resource conservation would include graphical composite curve and numerical targeting technique. Recent numerical targeting methods such as cascade analysis technique have thus far been proven the input linkage network. The two differences between synthesis problem of water and property based network with the gas network, while pure freshwater feed without contaminant has always been assumed to be available for synthesis of water network. It is quite common to encounter impure fresh feed for APT gas network. So this is the two key difference between gas cascade analysis, water pH analysis, and gas pH analysis. The second is the water network may consist of a mix of mass transfer based and non-mass transfer based process. Hence, the flow rate for water feed for demand may not be fixed. However, this is not the case for the gas network. So to maintain steady state operation, to maintain the system pressure in a gas phase, hydrogen reactor is necessary to maintain a uniform gas flow rate and gas position for a gas consuming process. So meaning the flow rate for the water is varied, but for the gases, it must have this certain level to ensure the gas is in steady state operation. So that is the two difference between water and gas pinch analysis. Okay, so the first example in this paper is the first picture. First one is the nitrogen integration. For nitrogen solution, figure one shows the process flow diagram of analytic tech manufacturing process. So what happened here is the coating ingredient are dissolved in an organic solvent and form a slurry mixture. The slurry is then suspended with a resin binder, a special additive. Next, the Scottish is distributed on a gas film, which in gas is used to induce evaporation rate of solvent that is proper for uh, deposition. A small amount of solvent is decomposed to other organic species in the coating chamber. The decomposed organic atom is separated from the coating chamber, exhaust gas using a membrane. The rotated stream system nitrogen and later with 1.9 organic solvent with denominated at the rate of 3 kg per second. The coated film undergoes a drying process where nitrogen gas is used to evaporate the remaining solvent. The dryer exhausts a flow rate of 5.5 kg per second and the solvent at the rate of 20%. The two-way exhaust gas stream are mixed and disposed of. To reduce nitrogen consumption, it is proposed to recycle, to use slash recycle the solvent-laden exhaust gas to the coating drying process subject to the drying process. So meaning this gas emission going back into the coating and drying. So for coating, the constraint is the gas flow rate must be between 2 to 2 kilograms per second with percent of solvent is equal to the 2.2. For drying, the flow rate is between 5.5 and 6, and the solvent is less than 0.5. So the outlet concentration for the coating and drying processes are assumed to be independent of the feed gas concentration. The constant listed above require the gaseous flow rate and its fluid concentration will need to fall within the given range. El Harwalgi and Fu et al. Specify two key strategies to maximize reuse slash recycle. First, the maximum permissible inlet concentration should be assigned as the limiting concentration, while the minimum heat flow rate should be assigned as the limiting flow rate. To see. Second, the source should be segregated into individual stream, since mixing tend to degrade the soft stream qualities. So for this example, the solvent-laden exhaust should be segregated into membrane-rotated and dryer exhaust gas stream. Fresh method nitrogen is solvent-free, hence has a utilization of 0%. So the purity of the nitrogen is high. The limiting data for the gassing resource are listed in table 1. So from this so from this process, we identify from this process only cutting and drying and membrane. So they find the gassing is 1, 2 for drying and cutting. This one is 5.5 and the coating is 3. The drying is 5.5. Coating is 3. What else? Membrane retentive here 3.9 and 0.5. So C enter, then C enter source outlet gas coil outlet sys. So for the drying and cutting here, so the concentration is given in that following constraint. So this is the constraint for the cutting and drying. So they choose the upper limit. So the gas cascade analysis. The first one you need to do is, okay, so I already define for you the table before stream. Sorry, yeah, stream. The gas cascade was the first step in conducting the GCA is to locate uh, the various gassing and source at their respective concentration level, as shown in tables 2. Oops. As shown in table 2, the concentration CK are arranged in ascending order. This one, instead of ppm, it's using a weight over weight percent. And the flow rate of each gas sink Fj gas source Fi is noted at specific concentration level K in column 3. Column 5 represents the net flow rate. This is 1, 2, 3, 4, 5. The next is to extend is to cascade the net flow surplus deficit. Hmm. Wait, okay. Hmm. You notice the difference between butter and yes. So ask you to calculate. Let me check that I can. Yes. Hmm. You notice it doesn't ask you to. Oh, it doesn't ask you to calculate purity. Yeah, and delta P. Okay, move on. So for Fj is the zinc equal to table 1. So the first one 0.1 is 5.5, 0.2 is 3, 0.4, this is for the source, 0.4 is 5.5, 1.9 is 3, 0. Okay. It does still have a Fp if water source demand. So we need to cascade the Fc, just tell you here. Level 5 is in this. So, okay, this is straightforward. What else is different? Eh? Water, you notice there is no negative sign for the zinc. Uh, So so if you do WCA, water cascade analysis, negatively. So, okay, instead of sum, it's negative, so minus since or demand minus source. So the negative between 5. Then you cascade it 0 to 0 is 0, 0, negative 5 till the end. Next is the delta n. Oh, okay. Okay, just this is from the paper. So it's explain the cascade principle in conceptual explained in figure 2. Let's say in figure 2A, without the nitrogen cascading, the 50 kg per second of waste gas is available as a gas source at an impurity concentration of 5%. That's one. On the other hand, gassing exists at 100 kg per second and can accept up to a impurity concentration of 10%. So if we don't consider the reuse of 50 kg per second of waste gas, we have to purge this one, while we need to add 100 kg of fresh gas to satisfy the sink for this process. So by cascading in figure 2B, by making use this 50 kg per second at 5% to satisfy the gassing that included a higher impurity of 10%, this one, it is possible to avoid purging the gas source directly as emission, and doing so reduce not only the waste gas generation but also the fresh gas. So at here 50, so the required fresh gas is only 50 kg, which is what we do. So for the impurity load is impurity load. Impurity load, we need to refer to page 5988 of the paper. This is paper of Fu and Manan. So the impurity load delta N is shown in column 7 of table 2, resulting from the product of cumulative gas flow rate FC. The concentration different across two concentration. Okay, so there are delta C here. Delta C is there, but there are no purity because the purity it's 1 million minus C over 1 million. This is straightforward delta C differences of the concentration. So let's say, okay, this one 0.1 to 0.2. So minus 0.1 over 1 to 0.01 delta C times FC, then you get delta M. Is it? Divide by 100 because of the percentage with the same times 0.6. Product of the gas flow rate is the concentration difference equals to concentration level and the one divided by everything. Okay. Missing 1 0. Okay. Then 0, 0, 0. Then you get 0.006 for the delta n. So for the delta m, so you do cascade for FC. So here you need to do cascade. Whereas you need to do cascading. Here as well, you need to do cascading. All right. The two final step in getting the minimum city target involves setting up the cumulative equity load cascade region. From delta m the column 8. So cumulative delta m here. Finally calculating the flow rate of fresh gas needed at each concentration level or the interval fresh gas flow rate FFK. The largest negative FFK which actually represent the minimum fresh gas target is cascaded down the cumulative gas flow rate column FC yield the minimum discharge flow rate. So cascading or three table to this invisible gas cascade table since they come M or cumulative delta M is negative. So it is invisible. You need to find a pinch. It's obvious. It's negative 5.625, the highest negative. This means that there is insufficient oh, okay. Insufficient gas at the respective concentration level. The amount of interval fresh gas flow rate is obtained by dividing cumulative delta M by the difference between the concentration at level K and the fresh fluid concentration CF. So FFK here is calculated by this equation. So come delta M negative 0.006 over CK. So CK is here 0.2. No? Minus 0 is 0. No. The absolute value of the largest negative 5.6. So the effect value of the largest negative FFK 5.65 is essentially the minimum fresh gas flow rate target FF. This amount is cascaded. This amount is cascaded down to down the FC column here. Feasibility intervention. So this is the feasibility for nitrogen integration. Each point at 0.4. Fresh gas is 5.65 kg per second. The minimum fresh heat and discharge flow rate required by the CA correspond to a reduction of 34% from the urgent heat and discharge flow rate one is referred to table 1. Because the discharge flow rate is discharge flow rate is 5.65. So the discharge flow rate for the original heat on the unmodified process is about 8.5 kg per second. Here it's 5.65 kg per second. With the original heat, in this case, in this process, the nitrogen integration, we refer to table 1. The scene require 8.5. Here it's just 8.5 and 60. That's how they calculate. Okay. The pin concentration for the gas network consists of 0.9. There is a 0 relative delta N from the meeting data in table 1. Emission from the drying process SR2. Okay, source number 2, which is from drying process, was verified as the pinch causing source for this example. To achieve the minimum gas target 2.875 kg of SR2. SR2 is 5.5 total up. Total, so 5.5 kg. So to achieve minimum gas target 2.875 of SR2, which exists between interval K3 and 4, here, should be located to the region above the pinch, because this is above the pinch, while 2.625 of SR2 between 4 and 5. Here. 2.62 of SR2 should be located below the pinch. So remember actually by rule of thumb, a rule or heuristic. The first heuristic is the do not hit of the source above the pitch, using the flash of the pitch below the pitch. So, okay, one is handbook of process integration, page 368. So the first heuristic, step 4, do not fit with water source above the pitch, to sink below the pitch and vice versa. This is also included what sources is minimum. The exact pinch causing stream distribution with the minimum cost target is termed as the resource allocation target. In the next section, a case study involving oxygen reuse factor will be pivoted to illustrate the design a technique to achieve the various targets. So now we know the minimum fresh heat in the transfer. The minimum fresh heat is 5.625. Minimum discharge is 5.625. Is where example, this similar paper is the oxygen integration. Some oxygen integration has focused on the optimum use of oxygen in a wastewater treatment plant. The following case study is an attempt to explore the interaction and possible site-wide integration between process and utility section for maximum oxygen recovery. The figure 3 shows a process plant that consumes a large amount of oxygen in its oxidation processes. A relatively small portion of the oxygen is also fed to enhance the combustion system, as well as for the aerobic section of the wastewater treatment plant. The source of oxygen emitted from the oxygen consuming process still of good quality and should therefore be used to reduce the uh, fresh fresh oxygen. This is the process. So we have 1, 2, 3, 4 for sing or divine resource. Uh, limiting data for all limiting data for all constituency and resource are given in total. Not that since TCA is able to handle impure fresh feed, 5% quickly in oxygen supply should not pose any problem in getting to the maximum gas flow target. The GCT for this case study in table 5, if a fresh oxygen supply and discharge target 40% to 4. Okay. They should prepare an invisible of exercise for you. So you prepare invisible gas cascade table gas conclusion in table 4. You will 15 minutes, you see that 15 minutes is not actually. We have 1, 2, 3, 4, 7, 8. 8 column. It doesn't require FFT. Yes. Focus. It's 1 5 p.m. We continue. Continue, do it. We continue. So to this, prepare this table. Try to table five. This paper by you always. Alan. So levels column one. So column one, two is column one, column two. It's actually the same, just following the table four, but you need to sort it in ascending order for the concentration because the when you calculated delta M here, then you need the delta C actually. So you add another column here. Another column here is for the another column here for ah delta C. So that easier for you to calculate delta M. So Fj, Fi is for the sink. Fj is for the sink. Fi is for the source. Normally sink first, then source. Then you do the Fi minus Fj. So yeah. So where do you get value for Fi and Fj? You get it from the flow chart. Figure 3. This is flow again, Fj. So from the flow chart, you need to create a limiting data for the table, guessing and guess source. So that table will give you this value here. Then, because the concentration start at 5%. When you read the details, for example, the fresh feed is not 0%. So this is the difference between water and gas. The heat doesn't necessarily 0%, meaning the highest purity. So in this case, there are some purity. So because there are no demand and sink for the fresh heat, so 0. And for the FC, the fresh heat is actually equal to 0 as well. Although there are value here, but for to to do a, you say, invisible WCT DCT cascade table. So we should start with fresh gas speed at 0. Then you cascading it, so 0, 0, 0, 35. So this one should be negative 35. Negative 35 plus 10 is negative 35, and so on until you get the FT how much. Then delta M is actually FC times with the delta C. Then we get delta M, then the cumulative delta N is actually a cascading again. So how many cascading? 3 cascading, including the delta C. So that is how you answer the question in the invisible data. So from there, once you get the cumulative delta N, and you see the highest negative will become the fresh speed. So in this case, negative 30 should be here in your table. You have to check the table, is it correct or not? You must get the pinch point at negative 30. Yes. So for GCT, for this case study, table 5, give fresh oxygen supply, FF, and discharge target at 30 kg per second. Discharge at This corresponds to a fresh oxidation of 27% and discharge oxidation of 73% as compared to the best case system shown in figure 3. So it's the figure 3. So we can reduce how much? 27% of this. 1 in reduction of, yeah, this one. Network design. So this section review the design technique for utility gas network. That alternative technique for water network design will also be applied in combination with the flow rate tanker and finish point established using the GCA technique. The pinch concentration identified in the targeting stage plays an important role in designing a network for maximum gas reuse/recycle. The pinch divides the network into two design regions: the region above the pinch and those below the pinch. For problem involving a single pinch, it is essential uh, to observe the pinch division in order to achieve the minimum current established during the targeting stage. In the region above the pinch, this is talking about generally. So in the region above the pinch, relative equality load surplus is less. Balance with load deficit. On the other hand, there is always accessibility load in the region below the pinch. The region above the peak is therefore controlling the overall gas product balance for the network, and hence is the most crucial part of the network. So if you look at the table, figure 3, table 5, so the change occurs in between 40 to 50. So meaning 40, yeah, 40. So 40% process 1 gases. So it happened at process 1 gases. The process 1, the discharge, that is the uh, pinch. Following the above observation in designing gas network, the gas source of the pinch, the external gas supply must not be fed to a gassing below the pinch. So gassing below the pinch, what is it? That one is you refer to the table 5. Table 5 below the pinch 40. So 50, 65, and 100. T, which is the process 2 source. 65 is the combustion and wastewater treatment. In the city. This rule, is it? But I think this rule will result in a higher fresh gas flow rate. This rule also applies during see. I'm referring to paper, uh, page 5989, second column, second paragraph. Following the observation in designing gas network, this rule also applies during mixing of different gas sources belonging to the different pinch region. The pinch crossing stream that exists at the pinch position is, however, an exception to this rule. Recall that part of the pinch crossing stream belong to the region above the pinch, while the remaining belong to the region below the pinch. The pinch causing stream, this is important. The pinch causing stream that exists at the pinch concentration, which is the oxygen integration, figure 2, happen at process 1 source, gas source. What does it say? The pinch causing stream that exists at the pinch concentration is, however, an exception to this rule. We call that part of the pinch causing stream belong to the region above the pinch, while the remaining region below. So meaning the what is it? This source SR1, okay, process 1 source, the outlet for the process 1 can be uh, recycled or reused for other part of the process, meaning it can be mixed with process 1 as well. It can be mixed to process 2 as well because of this method for the gas. So, I mean, although it's 40% concentration, 40% concentration at to process 1 thing is around 10%. Not sure how much the tolerance for the process 1, they did say, but yeah, it's possible. To maintain steady state pressure of the gas consuming process, we need to maintain a uniform gas flow rate and concentration at the inlet stream of the gas consuming process. The following guideline can be used to design that network. For zinc fluoride is FSRS can FSR FSK equal to FSK where Fij is the fluoride between source SR and zinc is K. This is a summation. Okay, this is the summation side. Gas contain C concentration. The source is similar. Equation 2 actually a constraint or limit setting the fluoride. The gas content required by a zinc which equals the fluoride of source I to be fed to zinc J is limited. The ability of zinc J. Any gas from a source that is not fed to a zinc will leave as a discharge stream. So equation 4. Okay, this is how it's. Okay. So the gas network, for example, 1 and 2, example 1 is for the nitrogen, oxygen, designed using the above publication shown in figure 4 and 5, respectively. The fluoride target as well as the gas allocation target for the pinch closing stream when defining the state targeting stage early last year. Noted during the design stage, the gas network should be designed individually for the individual pinch region. This is to avoid the gas source from being fed into seen in different design region as well as many and characteristic of this respective region. Okay. So yeah, although this is the pinch, the recycle it to the process one, process process two, to yes, going to the combustion directly, and some of it is goes to the wastewater treatment. Push the properly to top. We got the process to straight to the discharge. Wastewater treatment discharge unit. So that process is on one. All of them here for the this is the nitrogen fresh nitrogen. So for drying it's require 4.125. coating is 1.5. So that value is coming from table 3. Visible GT, for example, 1, 5.625. So we have to add it up is 5.125. The coating. So coating guessing is 5.5. Next reason, 3. Oh, you refer to table 1, page 5980. See coating is coating from for the fresh case it's require 1.5. So another is coming from this line 1.5 and up is 3. Now we need to determine from the table the pinch occurs in. Pinch occurs in 4, 0.4%. 0.4%. This is about nitrogen. 4% is the drying. So the drying source. So the drying source referred to this line. So for gases, pinch occur, sorry, stream occur at the pinch. You can use it to go above the pinch. For this case, it's applying to the coating and to the drying itself. So both is above the pinch. Oh, modify the value above and below pinch into the 5.6 method the stream. Find the value above and below pinch. Value above the pinch. I think we will told you the answer. This is the pinch. So process 2 is for example 2. This is the pinch product. Pitch stream in the process example 1. The value is 10 kg per second, 40%. This one is 5.5 kg per second. Refer to figure 1, figure 4. 5.5% 0.4% concentration. Yeah. All right. Now we go to example 3 for this paper. So for example 3, it's nice. The author give regeneration for the gas. Yeah, he give us 2 example of regeneration. First one is using membrane. Second one is using pressure swing and suction. Give me 1 minute, please. Okay, sorry. We continue. This is hydrogen integration. Since hydrogen is a valuable utility gas in crude oil refineries and petrochemical plants, hydrogen reuse recycle has been the subject of extensive research. Among the promising graphical tool to set the minimum hydrogen surplus diagram and the metal reuse recycle pinch diagram, which we require you to draw. Figure 6 shows hydrogen network case from August and Fowler. The secret one is figure 6, where the existing fresh hydrogen consumption at 207 mole per second. There are 4 hydrogen consuming processes in this case. In this case study, hydrocracker unit is HCU, naphtha hydrotreater HT, naphtha hydrotreater second HT, and diesel hydrotreater DHT. There are 2 hydrogen condensing facilities in this network. We have a catalytic reforming unit, CRU, and the steam uh, forming unit, SRU. So the import here, meaning it's a fresh gas, fresh hydrogen gas at 5% purity, which is impressive. It's, it's a pure hydrogen gas. These are the internal hydrogen source for the network, and their use is to be maximized before considering the purchase of hydrogen because hydrogen is specific. So unlike water, the the feed fresh gas here is having 5% grit. If you use fresh water, normally we just choose 0%. If the water meet the 0%, but normally it's water, it's kind of cheap, compared to gases. Limiting data for all hydrogen source and seen as shown in table 6. So source is here, seeing is easier. Source is incoming. Sorry, seeing demand is incoming. Source is the outlet. So table 6, note that the limiting data for hydrogen network cannot be directly extracted from the process. The layer such that in table 6, the detailed procedure to extract limiting data is method elsewhere. So in this case, the stream, the sink here refer to HCU 6. Oh, okay. You see it? It's different. How they get the value? For the HCU, that's why I said not that the linking data value cannot be directly accepted from the process product in such as that figure 6. The detailed procedure to extract the data is presented as well. Okay. That downstairs, I haven't checked it. From, from 34 is harvest and towel. Okay, calculated procedure, concentration is different. If you look at the figure 6 there, concentration for zinc for HCU should be 6.6%, 1%, and the flow rate is around 762. Instead of 762, it's 2495 more percentage. But NHT, NHT also different. Yeah, it should be 138, 20% only. And but sources from HCU in the figure 6, it's 69, but here it's 1,008, 1,801. Because okay, concentration is the same, 25% for CNHT here. It's 30%, but the whole set, the what is it? Storage is small second disabled. So for concentration of the sources is okay. It's correctly based on the figure 6. For DHT 27%, SRU 7, CRU 20%. So steam reforming unit produce lesser purity compared to crude forming unit. The result of GCA shown in table 7. So Table 7 shows the minimum fresh hydrogen target here of 268 per second and 102 mole per second for the discharge. This value agree with that reported by the graphical targeting rule. The graphical targeting rule is to check people by vessel value. So number 53. Yeah, we talk about send upload link. Okay. So the GCT identify the CNHT as the pinch causing stream. So here 30% refer to the CNHT. CNHT is the track naphtha hydrotreater. Then uh, from which 354.8 per second must be sent to the region above the pinch and 102 is below the pinch. To further reduce fresh hydrogen intake, hydrogen source can be facilitated for reuse and recycle in the hydrogen sink. The next section demonstrates how GCA can be used to effectively place the hydrogen purifier in the context of an overall process. So the last example, not the last example. For example 3, uh, provide us with regeneration. So for the hydrogen integration, the GCT without regeneration is actually we just do like figure 5 there. So 41 54 7 7. So the gas source from CHNT, this is gas, it is able to check this. We didn't get the network design, right? So based on the previous example, meaning CNHT here, the source, it can be diverted instead of going to fuel, can be inverted to other stream, including so further of the pinch point, because based on the table 7 here, the pinch occur at level K10. This is the last one. This is the last one. This is the last one. So meaning all the remaining stream at the sink or source is actually above the above the sink. So you can actually divert it to some place require this source. Okay. Good. Because in this paper, they didn't give the network design. They didn't- after you identify the minimum fresh gas discharge flow rate, need to design that with the modification. Where does this goes? Sorry, where does the pinch stream goes for use on the second? Oh, to first, okay. Hydrogen purifier. Hydrogen purifier manipulate the properties of the hydrogen stream to match the desired properties of hydrogen stream. Common hydrogen purifier include pressure swing absorption, brain separation, cryogenic separation. In contrast to a water regeneration unit that normally produce a single product stream, hydrogen purification unit typically separate single hydrogen feed stream into two product streams, one with an authority fraction rate of the other. The low authority product stream can either be reused in another hydrogen consuming process or something to the same process. Uh, High authority product stream is either purged or used as fuel. In the context of an overall network, hydrogen purifier may be placed above, across, and below the pinch, with purification across the pinch being the best option. So the last sentence, yeah, just point. So the best option is to treat the chip at 50%, 4%. So when dealing with purifier placement, assessment of the impact of changes involve repetitive revision of the flow rate, target, and pitch relocation. Such tasks can be quite cumbersome with the use of physical tools. The GCA technique, which is very amenable to computable universe, managed to overcome this problem. Or explanation for the membrane? Yes, yes. Given a gas sufficient membrane with a hydrogen probability of 95%, one possible option is to purify the portion of the pinch causing stream, CHNT. So the pinch causing stream referred to figure 6 is with flow rate of 457 mole per second, pressure 20%, lies below the pinch at 20% of the 102.52 mole per second to produce stream at 2%. It is from material balance calculation, the flow rate of cultivation product. The product of this high quality permit stream is 69.57 mole per second. The product of cultivation for the data stream are 32.95 mole per second and 31.11% respectively. So when you use membrane, although you get the purified gas, but they are retentive, meaning some of the gas will pass through the membrane and become purified. So the others will just flow across the membrane. So the one flow across the membrane, we call it the related tape. So the related tape it will have a higher concentration of impurities. Adding these two hydrogen source. So after the permeate stream from that, how they get this value? Not sure how they get 102. I see there a given, this is given a version with the hydrogen of 95%. The version is 2.5, the version of the pitch causing or a portion of the pitch. Because the pitch point for it is around 457, so they just treat some of it. So some of it total up is 1.252 mole per second. Yes. 1.252. You get the product stream at 2% of it. So you get 2% of 69.57 here. Where do you get this? After the filtration by the membrane. But although you get the high concentration, sorry, low impurities, hydrogen, but for the reductive stream, it has a lot, like 29% concentration of impurities and 32.95 mole per second. Adding these two hydrogen source at their respective concentration. So once you get that value, the T354, 54, yes. So you see here the table 8. This is regeneration with membrane. You see the value for source SRT, source of CNHT, which in table 6 it's 3457.4 because we treated 102.52 minus 457, you get 354.9. Adding these two new hydrogen source. So two new hydrogen source is the 2% and another one is 89.11%. Yes. Then you need to recalculate the process. So once you get this value, need to it's actually the feed is only sorry the feed is 5% fresh gas. So the incoming sorry, so the regenerated hydrogen is actually have better purity compared to the fresh gas. So meaning it is at level 1 here, be above the fresh gas, which is why you see the FF here is below the fresh gas. So what you need to do is to calculate again, starting with FF equal to 0 here, because the first time we do We don't have this concentration. Not concentration. We don't have its demand or thing for the fresh gas should be zero. Yeah. So 69, 0, 6 something here, this value. So for this table, the pinch occurs at the rated depth, which is the lowest. So meaning all of the other stream, the source of stream is actually under above the peaks. Yeah, above the peaks. Yeah, right? Not that the not that the permeate stream from membrane separation, 2% impurity is now much cleaner than the fresh hydrogen supply and is located at the highest percentage level of the GCT. Hence, the fresh feed and discharge product of the work is now 196.8. Yeah? Six eight point eight to 69.6. Okay. Hence, the fresh feed and discharge product of the are now reduced to 196. Note also that the pH concentration increases to the concentration of 89.11%. So, how much? Reduce from 268, 720 more per second. Reduction in ay, mana pula? 72, so 72 more per second. 700. Okay, that is for the membrane. Next is the next example is regeneration with pressure swing absorption connected to purify uh, connected to purify hydrogen, and this is one of the method as well to purify, sorry, to separate an azeotropic and zeotropic mixture. Azeotropic means the boiling point is almost the same for the material, so it's not easy to separate it using normal distillation. So you use just swing. Okay, so let us assess another hydrogen purifier. PSA unit with a hydrogen recovery value of 90% and capability to purify the hydrogen stream up to 0.1 purity. That is it's not basic, very pure. From material balance calculation, one obtained the product is a residual flow rate of 64 and 64.65 more per second and 7 more per second. With the residue security position at 81.05%. Resetting target using DCRNA gave a reduced fresh hydrogen flow rate of 200 mole per second, which correspond to a reduced discharge flow rate of 3.711 mole per second. compared to membrane is softer. Although you get very pure hydrogen. Note that in this case, the PSA has also purified the hydrogen source. The high level relative to fresh hydrogen supply. We can now conclude that so in comparison with the membrane, the fresh fit here, uh, membrane is better. So, uh, not that in we can now conclude that the gas separation membrane plays a more vital role in reducing the fresh hydrogen target in this network compared to the PSA. This is due to the fact that a membrane with a higher recovery of 95% as compared to PSA with a recovery of 90% generate an additional amount of hydrogen from the region of excess hydrogen below the pitch to the region of hydrogen receipt above the pitch. However, one should note that amplifier that give a higher recovery may not necessarily better. The provider that produce a product with higher quality, as in this case, for sometimes we better section addressing the real product of the gas. Examine this section in the next multi problem that follows. Okay. This is a medical tools problem. This is example 4. So table 10 shows the hydrogen source and sink data. For example 4, there are 6 hydrogen sink. So they will give the is it based on this? Okay. So this is different, although it's hydrogen, but it's different than example 3. There are 6 hydrogen sink, 7 hydrogen source in this hydrogen supply. In this case, has an equity concentration of 0.1%. So fresh hydrogen supply is here. So using GCA, the minimum fresh supply and discharge flow rate are found to be 125 mole per second and 90.96 mole per second. What is table 11 here? So when they do the concentration, sorry, when they do the GCT, this cascade GCA, use this analysis, they found that there are two limiting, there are two pinch, meaning the cumulative delta M turn 0 or to stream. Yeah. Not sure, is it source or 1.7 is the source one is R1. This one is 5% should be source. Yeah, source 4. Source 4. It's, source 1 is source 4. This is a typical multi-pinch problem. Two pinch are resolved in the GCT at equity concentration of 1.7 and 5% following the technology in the water network. The pinch concentration at the lower equity concentration of 1.7 is designated as the limiting pinch. Pinch that influence the overall gas flooded when any process changes take place. In problem involving multiple pins, program involving multiple pins, more than two design regions may exist. For example, three distinct regions exist due to resistance of limiting pitch at 1.7 quality and specific pitch at 5%. So we have this limiting pitch SR1, secondary pitch SR2, SR4. Utilizing resistance technique, one can quickly define the pitch positive and exact hydrogen equation for the hydrogen source in each of the design region. This can then be verified using the network design procedure discussed previously. One of the possible networks to achieve the various established network target is shown in figure 7. So you notice the method here. This method is actually sync sync curve annotation diagram. This is a sync. Okay, there are no sync source location. This is just a NAD method developed by Wan Alwi and Manan. So this method network allocation diagram. So the correct elimination of the limiting pinch is crucial in problem involving multiple pinch point and red pinches. Elimination of the wrong pinch point. So how to choose. So the first pinch is the limiting pinch. The second pinch is the secondary pinch in ascending order. The elimination of the wrong pinch point will result in missed opportunity during hydrogen network linking. This is particularly important for problem involving people pitches where the region above the pitch, middle pitch is the most constrained part of the network. The bottlenecking strategy will only be beneficial when the hydrogen source product is increased above the limiting pitch. Alternatively, okay, this is the second explanation. Alternatively, decreasing the need of the hydrogen sink in the region above the limiting pinch. Because we have two pinch now. Yeah. So for region above the limiting pinch, this is another area where quick accurate division of the true pitch point and correct target is special in gas network basis. Okay. So given the same hydrogen profile in oxygen example 3, we can now determine the appropriate selection of a that will reduce the overall hydrogen product of the network. GCT for purifying the hydrogen source using gas special membrane. Okay, it's going to table 12. So it treated the pinch 1.7 because when you choose where to because if you choose to use purifier to improve the purity of the gas, so what we need to do is we need to choose either above, below, or across the page. So based on this paper, it's recommended the best option is to just choose the page stream for the regeneration. So in this case, it's 1.7. So page occur at sorry, regeneration for 1.7. So they do if you use membrane, you will get a 2%, 104 here. Yeah, 0.7 is 1.3. Right, 8%. Note that the two decimal pinch with the at 5% have been removed. The minimum flow rate target for the option are the same as before regulation table 11. So what you notice here is there are no secondary pinch focus. Once we regenerate the pinch stream using membrane. In other words, no benefit is obtained by adding a new membrane solution unit into the network. This is due to the fact that overall hydrogen fluoride target are controlled by the most western part of the network, the region above the limiting pinch. Hence, the precise stream must achieve an 80% lower than the maximum for the fresh hydrogen flowing can be reduced. So the fresh fit is 125. So this is similar. Although you remove the secondary pinch, but the fresh gas is the same. You see that? Fresh gas is the same. It's 125. So meaning, yeah, there's no changes. Another hydrogen purifier in example 3 is to use PSA. So PSA was used for version was the PSA unit with the hydrogen recovery of 90%. Uh, resulting residue stream at 52.43 pt and projection containing 0.1 pt, which was lower than the limiting pinch. So that one referred to table 13. So the product is, yeah, it's very high concentration. Sorry, very high purity at 0.1. So match with the uh, incoming fresh hydrogen supply, fresh gas coming. So we have 120, then 97 for the product here. So the FF is reduced to 54.22 mole per second, and the discharge target of 19.98. Because of the reallocation of hydrogen source within the network, original limiting exponential pinches disappear. If you notice for table 12 here, the pinch is the same. Pinch place is the same. But if you use a PSA, it's actually goes to the lowest, which is the residue for the PSA. So meaning that all of the stream is above the pinch. Note that PSA play a more important role in reducing the overall hydrogen traffic in this network as compared to gas separation membrane. By purifying the hydrogen source in the region of excess hydrogen below the secondary pinch, PSA supply an extra amount of hydrogen to the region of hydrogen deficit above the limiting pitch. Because when you use a membrane, the concentration of the after the treatment is actually below the pinch. Yeah, and it is far from the fresh gas, uh, which is above the pinch. That's why it's doesn't necessarily happen. But if you use PSA, it can reduce the concentration up from 0.1%, which is similar to the concentration of the incoming fresh gas. It actually reduce a lot of fresh gas. It's common sense. Yeah. So, okay. So the conclusion here, the cascade also to report everything the minimum product water the gas network has been sent to the gas network. Gas cascade analysis level quick accurate determination of the minimum flow rate, each permutation resource location target for identity gas network. Okay. Appropriate creation of gas location technique can be systematically assessed using the GCA. Time left, but yeah, I have another example. Just it's a case study. This is a TVPA. It's a gas cascade as well, but uh, some tweak. It's a gas system cascading analysis based on the time-based insurance TVPA. So what does it mean? It's actually instead of using the concentration in what is it ascending order normally we sort it. So in this case, it's using a time base, meaning 1 hour. Normally it doesn't use the 1 hour, but it's just time slices number one until maybe 24 if it's based on hour. So 1 until 24 hours. Something. This is based on case study happened in Europe where they they have this biogas converted from a farm, and that gas can be used. It's several methods like generating electricity, or the gas can be used as for the NGV, natural gas vehicle, or just for the cooking as a cooking gas. Mhm. In this one, not from this. Okay. So what you have learned today is gas cascade analysis. Next week it's time-based 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 phase analysis for gas system cascading, similar to this latest week, but it's still using GCA idea, but the calculation is a bit different. There will be some other study. First. So what we learn here is the first is about nitrogen integration. So for the nitrogen integration, we do gas cascade analysis technique. So for this diagram, is only have two sink and two source. Two sink and two source with one fresh supply. So that fresh supply is actually under source as well. And we don't know the concentration to be determined. We determine it through uh, GCP, GCA. So the second one is the oxygen integration. So for the oxygen integration, the method is similar to the first example, just that it have more sink and source up to 6 or 7 fresh gas, fresh supply. So the method is the same. Remove the pinch, then there are network design. So for these cases, for the case of gas, you can actually reuse or recycle. So the difference between reuse and recycle is if the gas, then let's see, check the figure 5 in this paper, page 5990. So the recycle here for the process one, the pinch occur at the source 10 kg per second, 40%. So the recycle means it's going back to the process one at 3.57 kg per second. So for the reuse is actually going to other processes. Sorry, that's what the chicken part. Yes, okay. So yeah, then for the hydrogen integration, this is good. They have two example of different regeneration. And PSA, just being consumption. So for the hydrogen integration, for hydrogen integration alone without the regeneration, the amount of uh, fresh uh, fresh hydrogen supply is 268 mole per second. But before the GCT, the actual one is 277. So 277 minus 268. The reduction is around 9 mole per second. It's not that much. It's not really saving. So by regenerating the pinch here, it can reduce the fresh supply up to 126. So there's 126. This is for membrane regeneration. Can save the company the process 81 mole per second. Then we have another one is using PSA, but uh, the regeneration PSA it will save around 77 mole per second. Next is the multiple pinch. This is still using the hydrogen. Not sure how does the network look like. It just give you the table 10 here. This will be source. So, but when we do the pinch, we encounter two pinch. The first one is the limiting pinch, second one is the secondary pinch. So what we need to do is to uh, regenerate the pinch. So in this case, it will generate the pinch, the limiting pinch. By regenerating with the membrane is actually didn't really have the fresh gas supply is still the same as the GCT without the regeneration. And by using pressure swing absorption because of the oh, sorry, high quality of the PSA, it actually reduce up to how much? Hydrogen supply 1.5. by 71 more percent. Yes, yes. Fresh hydrogen can be so it's called those who haven't children can check in. So we meet again next week. Next week is April. Yeah. Saturday this week. Yeah. So thank you. Location, okay. So next week we get again. We learn about GCA for TVPA. For my part, for the final exam is actually about test analysis. This week.